Can you see my screen?
Oh, yeah. Yeah,
Yeah.
I can see that. Nice.
Awesome.
Okay, so it's almost 10 a.m. and we can start maybe, just right now, and maybe more audience will come in soon. Yeah, so hello everyone. Welcome to today's Web3BuidlerTech technical sharing session. Today we have invited Sam, his Russian CEO, to give us a feature talk about the surge scaling Ethereum to 100K TPS. Yeah, so you can start.
Okay, great. Thanks, Yo-Yo.
Thank you.
All good. Is my mic okay? Can you hear me all right?
Yes.
Okay, cool. All right, I will get into it then. So thanks for having me, everyone. I'm, like Yo-Yo said, I'm Sam, the CEO of Rise Labs. We focus on Ethereum scaling, and specifically what we're working on is building a high performance layer 2. So today I'm going to talk a little bit about what that means, kind of the current performance landscape today and the activity we see in Ethereum. Then I'll dig into what needs to happen for us to reach high performance. Like what are the bottlenecks today? And then I'll close with a few use cases and some of the interesting stuff that we can look forward to once some of these high performance layer 2s come to market. So yeah, let's get into it. So the first thing is the surge. So the surge is one of Vitalik's many urges. This comes from his latest roadmap, and aligned in parallel to this, we've got the merge, the purge. The surge is one of them, and a couple others. The real goal of the surge is to reach 100,000 transactions per second on an individual rollup. So Vitalik and the Ethereum research community believes that this is the target that we should be pushing towards to unlock some particular use cases that really need this kind of performance. So one interesting thing about the surge is it focuses mostly on data availability. And so data availability is one key component of the surge. Of reaching high performance rollups, but there are other aspects other problems we need to solve. So I'm going to touch on those today. Another thing I just want to note is that today, high performance is really only possible with optimistic rollups. The performance of optimistic rollups is just far more than ZK. ZK has a massive bottleneck when it comes to generating the fraud proofs. We're nowhere near real-time fraud proofs, and we're nowhere near 100,000 fraud proofs per second. So today's focus is going to be on optimistic. I do see a future where ZK EVM or ZK fraud proofs, sorry, not fraud proofs, I mean validity proofs. That's what I meant to say. Validity proofs get to the kind of performance that we need in ZK today. Awesome. So this is my new favorite website. This is rollup.wtf. It's been built by Conduit. Conduit's a paradigm-backed RAS provider. They built this app that shows you the real-time activity across the rollup landscape. So the interesting figures are the transactions per second, also the mega gas. So I highly recommend jumping on this. It's a bit of fun to watch, kind of like real-time how the ecosystem is operating. But let's look at the sums. So if we combine all of the activity across rollups today, they typically average about 200 TPS per second. You compare that to Solana, where Solana has around 2,000 TPS per second. So there's a 10x difference between all of the rollups, so the 40 plus rollups that exist in Ethereum today, and a single high performance L1. So I think this is interesting because the gap, there's clearly demand on Solana, so there's demand for more performance, but there's far more devs and activity in the Ethereum landscape. So there's value in closing this gap. So we just in a simplified view of what that looks like, when builders are building, they've got to make a decision. Should they build in Ethereum, where the vast majority of the tools, the builders, the infrastructure, like the wallet support and integrations, as well as users are, or they can go to Solana, which optimizes for speed and performance. Solana's done quite well on the infrastructure and users. Notably, Solana is probably the only other virtual machine, only other layer or blockchain that's been able to introduce a new virtual machine to the industry. And I think why this slide is particularly interesting is that Solana was able to grow against the headwind of Ethereum by just focusing on performance, by filling this gap. I think that really highlights how powerful performance can be. And beyond that, I think there's two key reasons why high TPS, high throughput, and low latency is important in the blockchain for blockchains and for industry in large. One is scale. We're just not going to reach a scale without it. The other is user experience. So let's double click on these. So for some context, these are some like rough estimates of the kind of TPS you need for Web 2 or like traditional applications. So the NASDAQ, it needs about 1.2K transactions per second. And I believe this is per market as well. So one individual, say like one individual stock, for instance, needs this kind of performance. Visa, 6.5K, X, 10K. So if you wanted to have a fully decentralized on-chain social media site similar to X or Twitter, you need 10K performance minimum. And then Binance, the throughput it needs to support market makers is in the ballpark of the 100K TPS or above. So blockchains today are nowhere near this. Like I said, Solana's at about 2K. All of Ethereum rollups combined are at about 200. So we've got a long way to go before we unlock some of these additional use cases. And then the second thing is user experience. So some of this thing is obvious, but there's some interesting properties. So cost, obvious one, there's just applications that are no longer viable once blocks cost a particular price. Gas spikes are a particular nuisance when the users run into gas spikes, and which leads to user attrition. So this is one factor that sometimes you just can't use a chain because there's the fees are spiked too much, or the network can't handle the capacity. So I think this is an underappreciated problem within the ecosystem. We can't just put up with it, but in the future we need to solve this so our UX doesn't decline. If the price of petrol went up by 10x one day, you wouldn't be driving your car. So I think it's an interesting use case. The other is fragmentation. That splitting the projects and the liquidity across many different chains is a problem. So that's an issue that needs to be solved. And by building individual high performance chains, they don't have the fragmentation problem. So yeah, all of these things lead to user attrition. So every time the blockchain industry gets some headwind and users come into the space, we have these anti-network effects that lead to users coming, having a bad experience, leaving, and then also sharing their bad experience with other people that inhibit more growth. So I think we've got a real problem in the space, and so scaling and performance needs to be a serious focus. And one notable mention on fragmentation is just an example of where solving performance really unlocks some strong network effects. So one of the biggest problems for applications or projects in Web3 today is user distribution. So how do you get access to your users? One really interesting thing about Uniswap is that they've done very little on their user distribution. They've been fortunate enough to lean on all of the apps that build on them. So Uniswap has aggregators, wallets, vaults, and soon to have hooks projects for UniV4 that launch tokens, raise money, build new products, new applications, all of which are attracting users and liquidity towards the Uniswap product. So this wouldn't be possible if Uniswap was sitting on its own chain. This is a benefit from having a high capacity within a single chain that allows, enough capacity within a single chain that allows builders to build on top of each other. So this interoperability and the opportunity for DeFi Legos is a real benefit to chains, and fragmentation at the moment is really inhibiting that. And I think that's a big part of why Solana's been doing quite well. So what does this look like in the modular landscape? I really like the city building analogy. So I see what we're building at Rise and what a high performance layer 2 is like building the Burj Khalifa in New York City, or more so that the rollup ecosystem will gravitate to a kind of a similar map to New York City, where you have a few very high capacity rollups that have the vast majority of the liquidity and activity, and then a large suite of app chains that have application specific purposes that leverage the liquidity from those chains. So today I see the ecosystem as the modular ecosystem in Ethereum looking more like Paris, like quite flat, not very high performance, but where we're going is something more like New York, where you do have the sky rises and then the sprawling urban area. But yeah, how I see Rise is where we're trying to build the Burj Khalifa. So how do we get there? I'm not going to dig into this. I don't want this talk to be too technical. But this is at a high level what the roll-up anatomy looks like. Users send transactions via an RPC node. This makes its way to the execution client, which sits in the mempool. Consensus fetches transactions from L1. It decides when it wants to create a block, requests a block from the execution client. This executes the block, creates a Merkle root, and then sends it to the proposer and the batcher. The proposer will submit the state commits. Batcher sends the block data. So the two parts that are important here is the execution client. It needs to execute the transactions. And then the other one is the block data, this is where the data availability goes. They are the two main problems when it comes to throughput. So yeah, let's look at this. Where are the bottlenecks? So data availability is the first one that pops up. Execution is another. So this is just the raw speed at which you can execute the raw EVM transaction. And then state access is the final one. So how fast you can read the state from storage and how fast you can calculate the Merkle root. And I'll dig into this a little bit. So for a long time, data availability was a bottleneck. Thanks to external solutions, it's no longer the case. So let's dig into what that actually means and what the kind of numbers we're looking at are. So if we look at the inbound being like transactions coming in, native transfer is about 110 bytes, ERC is 164, Uniswap is 260. So ballpark 1 to 300 bytes per transaction. Some with a lot of call data get a lot bigger. Now let's look at the capacity. So Ethereum without blobs, if you were to use the entire block, it has about 150 kilobytes per second of capacity. This is obviously not realistic because using the entire Ethereum block would be extraordinarily expensive. So take this value with a grain of salt. And there's Ethereum blobs. So this is what we know and love today. 6 blobs per block every 12 seconds amounts to about 64 kilobytes per second. So this is like dial-up internet speed or a little bit faster. So we're still like in the 90s or 2000s when it comes to Ethereum's throughput. And then Celestia, which was kind of the first external DA solution that really gained some traction. Currently, they're at about 2 megabytes. They plan to go up further, and EigenDA is the fastest on the market that I'm aware of. There are some other competitors that claim to be faster, so take also do your own research there, but they're sitting at about 10 megabytes per second. So let's take a look at what that means if we can with these kind of performance levels. So for native transfers, if using blobs, you can hit about 600 TPS, and that is if you use all 6 blobs every block. So interesting thing about that, if you did that, the fees would slowly climb, and that would only support one single rollup. EigenDA, on the other hand, can get about 95,000 native transfers. So we're getting very close to this 100K number. This 100 bytes is actually the uncompressed value. So when it's compressed, this will be smaller. So what I'm getting at here is that EigenDA unlocks this goal of hitting 100,000 TPS. EigenDA and other DA solutions will continue to grow in their capacity, but this is a really great indicator that we can get there, get to this initial target today. So yeah, data availability solved for the meantime. I think ultimately everyone's going to use Ethereum DA, but that's just my opinion. For the meantime, a lot of people are going to use external DA solutions. The next challenge to tackle is really execution. So there's a few ways to tackle one. One I'm going to talk about today is parallel EVM execution. And that's something we do at Rise to really speed things up. So what does a typical execution pipeline look like? So you've got, let's say this is a block with 3 transactions. They would usually be executed sequentially. So you just execute one, then the other, then the other. And all while you're updating the state and having like a state in cache, and then you update the state every time you do the transaction. The output would be the state diff at the end. So input transactions, output state diff. So we can do the same thing, but execute in parallel. So input is the block, so the transactions, output is the state diff. But the difference being is that we send each of the transactions to a different core in the CPU to execute the transaction. And then you have a secondary state where you validate that there were no dependencies between these transactions. And if there are no dependencies, it means that this was can be validly executed. It means you have the same deterministic outcome from this as if you were to execute sequentially. So I think you can see here how this can really speed things up. This, for context, this approach of optimistically executing it comes from a research paper from Aptos called Block STM. It's since been adopted to work in the EVM environment, and it's still a really interesting space. There's a lot of ways to improve this. So an example of where the validation step fails, so say there was a dependency between transaction 2 and transaction 3, this would trigger a failure. So in this case, you'd need to re-execute transaction 3 and then revalidate. So there's actually circumstances where parallel EVM is slower than sequential EVM. There's various ways you can tackle this, and we are tackling some of these at Rise. We've built an open source parallel EVM engine. We've built this compatible with Reth. If you're familiar with it, Reth is the execution client that's been built by Paradigm. We're planning to upstream this into Reth. So we're hoping that our parallel EVM engine will be the default parallel EVM execution engine for Reth. Some of the things that we're doing beyond just parallel EVM and the typical block STM approach. So we're doing some stuff that anticipates when there will be a dependency collision. So we're doing some static analysis on the block input. It gets pretty technical, so I won't bore you with those details. But yeah, we're doing static analysis on the input, and then we're also doing some fun stuff with atomic state updates to make particular transactions more parallelizable. And we've got to the point where pretty much any ERC20 transaction we can execute in parallel, which has been a massive unlock. Where that's put us today is for large blocks, where our benchmarks are showing that we're getting about a 13 times improvement. So something that would have taken 20 seconds is now taking less than 1 second to execute, which is really speeding things up. And they're just rough numbers. Nothing really ever takes 20 seconds. Cool. So 2 pieces of the bottleneck, of the throughput bottleneck solved. Let's look at the last one. So state access. State access is, for context, the Ethereum state is stored in what's called an MPT, so a Merkle-Patricia-Trie structure. So every address is a leaf node in a Patricia tree, and to find that leaf node, you essentially have to look down the tree. So for Ethereum, because it's got quite a large state and quite a diverse state, you've got to do between 8 and 9 hops to actually get down to your tree node. So the problem there is that each of those hops is an IO operation to your SSD. You have to read from your SSD to fetch each of these intermediary nodes to find where the next node is. This is essentially like a long linked list, and it's typically stored in a off-the-shelf key value store, such as LevelDB or PebbleDB, for instance. So that makes these steps extremely, extremely slow. And also, once you find the leaf node, often that points to an estate tree for the address, and you've got to traverse down another tree. So yeah, there's a lot of inefficiencies in this. So there's a few things you can do to tackle this. One thing that we're doing is it's called layered MPT. This is actually where you split up the MPT tree into 3 trees, 2 of which stay in RAM, 1 stays in the SSD. This allows us to store the most readily accessed data in RAM. So RAM's faster, much faster than accessing the IO. So it means we can access it faster, but also means because the trees are smaller, we can do fewer hops. And there's some funky math that goes on into being able to concatenate these trees to generate the Merkle root that ends up being faster as well. So that's what we're doing that's one thing we're doing. Some other stuff you can do, which I don't have a slide for, unfortunately, is modifying the database to build native databases that are more tailored towards MPT tree structures. So today what's used for trees are, like I said, Pebble and Level DBs. These are just off-the-shelf databases. What you can do is build custom databases. There's a particularly interesting one called NOMT, N-O-M-T, that a team's working on at the moment, where they leverage some inherent properties of the SSD. It's actually called a binary MPT tree, where each of the nodes, where you can fetch multiple nodes in a single request because they're sitting in the page of the SSD. But I won't dig into that too much, but the bottom line is there's some really cool work going into really trying to speed up the state access for EVMs. So yeah, they're the three bottlenecks. With these, essentially what we're working on, what we've reached in our internal testing, our internal DevNet, is that we've made it. We've reached 100K TPS. We're pretty excited about this. There's going to be some huge unlocks. I really see how the industry will progress is that there'll be kind of two categories. There'll be the generation 1 rollups, which are the rollups we see today, like Optimism and Arbitrum. And I see generation 2 as the rollups that go from this like 200 to 500 TPS to 100K TPS. Like that's a big paradigm shift. So I think high performance rollups will be considered like generation 2 rollups. And they're going to unlock some really interesting applications and going to allow for some like quite large ecosystems and quite active ecosystems for various applications. But what about the apps? Like we've got the tech. Let's take a look at the particular apps that this high performance stack and high scaling in Ethereum can unlock. So performance unlock. The first one is one that's dear to my heart. Previously, I worked on HFT trading, market making in some centralized exchanges in crypto. And one of the things I'd love to see one day is essentially the activity that's happening on centralized exchanges on like Binance, Bybit, Bitfinex, that kind of thing, to be possible on chain. And in my opinion, the biggest limiting factor to unlock that today is really performance of the chain. The infrastructure just can't support it. So interesting detail about the volume and activity. So a vast majority of the trading volume is on CeFi today. So like 99% of trading happens in CeFi on Binance, Coinbase, etc. There's very little is actually on chain in DEXs. And DEXs, the reason for that is DEXs are really good. So AMMs, automated market makers, are brilliant, absolutely brilliant at bootstrapping liquidity. So if you have a token that doesn't have any market makers, doesn't have any liquidity, you can have a liquid market in a few clicks if you have enough capital to back it. So that's great for bootstrapping liquidity, but it hits a certain point where it becomes inefficient relative to a central limit order book. So central limit order books are kind of the difference. Central limit order books are great at high efficient market making, high efficient swaps, but you need to hit a certain volume or a certain traction before it's actually viable. So it's really hard to bootstrap, but really efficient. And there's a phrase I hear a lot is liquidity flows to where is most efficient. So if we can offer that kind of infrastructure on chain, I think there's an opportunity to really soak up a lot of the volume and activity that's in CeFi today and bring that on chain. I think that's super exciting. Like the UX that you can build on chain for a central limit order book DEX is better than the UX you can provide off chain if the performance allows it. So really exciting use case. Another one is SocialFi. So this is the idea that we like the Twitter on chain or like YouTube or streaming services on chain. Right now, Firecast is the most successful decentralized social media network or SocialFi project. A lot of what they do is actually off chain. So when you're interacting with Firecaster, you're interacting with their centralized servers, and then it's the centralized servers' role to bundle things up and submit hashes. So there's a world where you could build all of that on chain, and there's a lot of benefits to this. I think the open interoperability of smart contracts allows for some really interesting innovation when it comes to SocialFi. Also makes it censorship resistant. Have much better liveliness guarantees, and also means you can build kind of whatever whatever user interface you want on top of these social graphs. So I think that's super interesting. And the final one I'll mention is Web3 gaming. So we're kind of in gaming at the moment, we're kind of at this spot where a lot of games are like partially off-chain. So it's like Web 2.5. They seem to be the most successful games so far. And whereas fully on-chain games are starting to make some traction. One of the limiting factors for fully on-chain games is that you need more performance. You need more block space capacity to get there. There's probably been 10 examples where on-chain games have brought a network to its knees. I think there was like a crab game on Avalanche, for instance, that just meant Avalanche was unusable for a period of time. And there's a few other examples of that. So I think Web3 gaming is going to be a huge unlock. So these are just three of like the headliners that are pretty obvious, but I think there's going to be a wealth of like unexpected applications that are unlocked through performance, things that we haven't thought of like yet, or iterations of existing things, like very, very actively managed strategies on chain will be unlocked. Like right now, active strategies on chain are just far too expensive to run, whereas that will be unlocked with enough capacity and enough throughput. So yeah, I'm excited for the future of high performance in the layer 2 landscape, and even more performance than we have seen in blockchain yet is on the horizon. So we're at the verge of that hockey stick of where we see performance really ramp up in the blockchain infrastructure. So yeah, that's everything. Thank you. Please check us out at Rise. We're putting a lot of effort into building this out. We've got a really strong team, and yeah, keep an eye on our progress. Please get involved in the Discord. We're hoping to build quite a strong community and onboard some great builders. So if you're a builder interested in building some high performance apps, got some interesting ideas, hit us up. We're keen to really back and put our full support behind some great teams. That's all.
Cool.
Thanks,
Thank you. Thank you.
Thanks, yeah.
Thank you, Sam. So yeah, so anyone have questions, we can ask here. And I think Chi has asked one question in the chat. So he asked for 100K transaction per second. What kind of transactions per second, and what is the state size? And Uniswap DEX is notoriously unfriendly to OP or parallel execution.
Yeah, cool. So two questions here. One is the state size, and for high performance chains, the state size is a serious concern. Fortunately, we're building on Reth, and Reth's current Reth is extremely efficient when it comes to storage. So right now, I think the base state size is about 4 or 5 terabytes when running with Geth. However, if you run that with Reth, it's about 10 times as small. It's just because the state structure or the database structure in Reth is much smaller. So that gives us quite a bit of wiggle room there. But there's on the state access, on the state size and the state bloat problem, there's ways that you can tackle this with like pruning or like state rent, so that essentially users have to, or users or protocols have to pay for the state of their application or their address. We've seen this in various other blockchains, and it seems to work relatively well. However, to do it, you have to break EVM compatibility. And we're pretty hard-lined about maintaining EVM compatibility. I think the second you add friction to builders or wallets and infrastructure, it's going to end badly. So our approach there is that we want to work with other teams in the rollup ecosystem to help kind of pioneer these changes. Getting this stuff into Ethereum is going to be extremely slow. Building this in the layer 2 landscape is an opportunity for us to accelerate some of these changes. So I'd really like to see things like state pruning live in some of the bigger layer 2s and Rise well before it makes it into Ethereum, so that we can set the standard. As for Uniswap DEXs being notoriously unfriendly to optimistic parallel execution, yes, that is absolutely correct. The reason being is, for context for everyone else, Uniswap is like say you've got multiple people trading with an individual pool. So you've got 2 tokens in a particular pool. whole bunch of addresses interacting with these two tokens. That means there's a pretty clear linear dependency between every transaction that's interacting with this Uniswap pool. So what we're doing there, which is actually some pretty interesting tech and has proven to be really, really successful, is that we're doing something called atomic state updates. So if you bring it back to the ERC level, so say you have an ERC transaction, say I'm sending tokens from myself to Yo-Yo, 100 USDC. What happens on the state level is you see the balance, my balance drop by 100 and Yo-Yo's balance increase by 100. And then say in the same block, Yo-Yo sends 20 USDC to her friend. And so her balance drops by 20 and her friend's increases by 20 as well. If you were to execute these in parallel, there'd be a collision. But what you can do is, rather than the output of the PEVM engine being the state update, so the absolute state update, so you say like from 0 to 100 or 20 to 0, you change it so that you're doing an atomic state diff or an atomic state update, so that it's like a plus 100 and a minus 100. Rather than the absolute values. And then you can do a validation steps, sort of like where you can concatenate all of these values. So it means Yo-Yo's balance diff would be plus 100 and minus 20. So she'd end up with an 80 and I would have a minus 100, for instance. And this is a way where you can make particular transactions like Uniswap dexes or LP pools. You can make those transactions parallelizable. And we've done this, so feel free to check out our public PEVM engine, and it's working. So that's pretty cool. Any other questions?
Yeah. Oh, sorry.
Cool.
Yeah, please.
Oh, sorry. Okay, I'll answer this one from Kobe first. So can you evaluate latency if you increase TPS but reduce latency? Is it worth that effort? Do you mean increase TPS but increase latency? I suspect that's what you meant. Yeah, cool. So fortunately, we can there are some limiting factors. Like if you try and reduce the block time with really large blocks, there is like some negative impacts there. So there is risk of needing to increase the latency, but we're doing something interesting to tackle this. We're doing something called, we call it continuous executions, where we have a thread that's continuously executing blocks. It's managing the execution of the like parallel execution. So what we do, rather than executing an entire block at a time, say we've got a block, a 1 second block that's 1 gigagas worth of transactions, we slice that into many blocks. So say we have 100 or 1,000 blocks within that period. And that means that we essentially continually pull from the mempool, or we just receive transactions on the fly. We execute them in a partial block, and then we provide the pre-confirmation, the execution pre-confirmation immediately. So it means if the block time is 1 second, the pre-confirmation latency might be 10 milliseconds, for instance. So that's going to be quite a massive unlock, that our latency is actually going to be far better than many other L2s today. So yeah, we found a way to tackle that. We're looking at 1 second blocks. We'd like to hit 250 millisecond blocks. We're still testing to see if we can make that happen. I think Arbitrum's done a great job at really pushing the envelope here, but we'd like to have low latency through continuous execution and like shorter block times as well. Next, do we have another question?
Yes, I do have a question. Thanks a lot for your presentation. I was just wondering, what is the status of your chain at the moment? And if you think about recently, I think Monad has made a lot of noise. How should we think about the difference between your chain versus Monad in terms of technology?
Yeah, thanks. It's a good question. So our progress, we've been building for about 8 months now. We've got a relatively small team. There's about 8 of us, 6 of which are engineers. Of our stack, we've built the execution component, and we're building out the state access component at the moment. So that's kind of past the research phase, and we're digging in pretty deep. We're planning, we'll have a test net this year, and we might even have a mainnet this year. That's still up in the air. So we're progressing. We plan on getting this to market pretty quick. Monad's been building for a lot longer than us, but we've got the benefits of being in the L2 space. You can iterate a lot faster as an L2. And yeah, as a comparison between high performance L1 like Monad and ourselves, I think you probably like say V2 would fall under that as well. I think there's some really interesting tech. The one challenge that they have is that they're not in the Ethereum ecosystem. So they don't have the vast support of the Ethereum ecosystem, nor the liquidity that's already here. So proximity to Ethereum has proven to be quite successful or quite valuable in the past. If you look at Arbitrum and Optimism, in the early days, they didn't have a token. They had a worse user experience. They had slower block times and more expensive transactions than their competitors, such as Phantom and Avalanche. However, they were able to grow faster, grow against Avalanche and Phantom. And a big reason for that is A, Ethereum alignment, and B, just proximity to Ethereum. Ethereum is where a vast majority of the TVL and activity and whales and users are. So proximity to Ethereum makes a big role. And I think that's the advantage that we have against some of the high performance L1s. It was a no-brainer for us. Like, we considered doing an L1 or an L2, and we dug into it and ended up being a no-brainer. That said, Monad has a killer community. There's no denying that. So they're going to have quite a strong distribution, but I see it as more like Monad versus Ethereum than Monad versus Rise.
Thanks. So that's probably more about the externality, right? How about technology?
Cool. Yeah. I can talk to the technology. So Monad's tech isn't public, but I can speak to what is public. So they're doing parallel EVM. I know they're doing block STM. I'm not sure about how deep they've gone into extending block STM like what we have. As far as we know, our public parallel EVM engine is the fastest EVM execution engine available today. So that's pretty strong. They're also building a custom DB. They're probably a bit more progressed than us. They've been putting a lot of time into this, and they've actually changed the state tree for their custom DB as far as I'm aware. So on the surface, like the tech is similar. We're solving similar problems, just in different domains. They're solving those problems in an L1 landscape. They have the overhead of consensus and networking. We less so for us, because we're layer 2, we can have more centralized sequences. So initially we'll have a single centralized sequencer with some redundancy, but eventually we'll have multiple sequences, and we're looking into based sequencing for our decentralization strategy there.
I see. Thanks. And you mentioned you have achieved 100,000 TPS, and this is under what kind of environment?
So we're not quite at 100,000. We're at 40K transfers for native transfers, but we're confident we can get to 100,000. And this is in a local dev environment. So there are some networking overheads that we need to test for as well. But we're confident we can hit 100K by the time we hit mainnet.
Mm-hmm. I'm kind of wondering if you are if you're reaching like 100K TPS, isn't it more, in terms of the use case, right? I think payments would be the largest use case for that, and not even in the blockchain space, but overall payment space. That would be huge.
Yeah, right? I think so. Interestingly, and this might change with like micropayments or streaming. Interestingly, we have here is that Visa came up as, from the research I found, was about 6.5K TPS. I suspect that grows. Like Visa doesn't covers a large population, but it's not like a large portion of the like micropayments around the world. So yeah, I think payments will ultimately need that like 100K or plus performance. So we're pretty keen on working with some teams. Like I've actually got a call today with a team that's built out remittance network, and so that kind of stuff I think will be really interesting. And like the podcast 2.0 payment streaming, we see that with the Lightning Network of all things. But that could be a really interesting use case for high performance as well, for like streaming to creators that you enjoy watching, that you can like set up a constant drip while you're watching their feed, for instance. So yeah, I completely agree. It's a really cool use case.
Great. Okay, thanks a lot for your time.
No problem. Thanks for the questions. Any other questions?
Maybe would you remind me what kind of rollup are you using?
Will be an optimistic rollup.
Okay.
So yeah, a lot of our code was in like the rollup specific consensus code was inherited from Optimism, and we've changed a lot of it to make it work under like in a higher performance environment.
Cool. Thanks.
Just realized I have my camera off this whole time, so yeah.
Any more questions? Yeah. Please ask directly. If there's no more further questions, then thank you, Sam. Thanks for coming and share the how RiseChain works, and thanks everyone for attending. Yeah.
Well, and thanks for having me on, and it was fun to share what we're building. And feel free to hit me up if anyone wants to hear more.
Okay.